The integration of neural networks with logic programming has been a significant focus in the field of Neural-Symbolic AI. This approach aims to combine the strengths of both symbolic reasoning and neural networks to enhance learning capabilities, particularly in scenarios where direct supervision is unavailable. Welcome, folks. It's time for another engaging episode of Elite Ledger Media. I'm your host, Mark Johnson, joined by the insightful Ivo Kausen. Today, we're diving deep into a fascinating fusion of AI and logic programming. Ivo, could you kickstart our conversation with a bit of context?
Absolutely, Mark. We're discussing the paper titled Differentiable Logic Programming for Distant Supervision. This paper addresses a significant focus area within Neural-Symbolic AI, or NeSy. The researchers are essentially combining the strengths of symbolic reasoning and neural networks to spearhead advancements in learning capabilities, especially in scenarios without direct supervision.
Broad terms there, Ivo. Could we delve a bit deeper? Let's start with differentiable logic programming. What's the novelty here?
Of course, Mark. Traditional logic programming depends heavily on symbolic solvers, which can be inefficient and computationally expensive. However, this new approach, by embedding logic programs and neural network outputs into matrices, opens doors to differentiable evaluation of logical implications and constraints. It's essentially using a gradient-based optimization technique that makes learning more efficient and handles noisy data or missing labels in distant supervision scenarios.
Interesting. Could you elaborate on how this methodology addresses distant supervision?
Interesting question, Mark. Distant supervision is primarily a technique used for generating training data. This method uses existing databases, like Freebase, to automatically annotate large corpora. It's useful when manual annotation is impractical. However, it can lead to noisy data. The novel method we're discussing counteracts this by allowing for more robust evaluation of logical implications and constraints.
Fascinating. So there's potential for increased accuracy. Speaking of which, how did this approach fare when evaluated against existing ones?
So, the method competed favorably, Mark. The results indicate that not only did it match or exceed the accuracy of existing methods, it also sped up the learning process, which is really exciting for the realm of NeSy applications.
Impressive. Let's shift gears now, Ivo. What does this mean for the future? Are there any potential applications already in view?
Indeed, Mark. There's a lot brewing. By enabling integration of neural networks with logic programming in a differentiable manner, there are new possibilities for learning in scenarios where direct supervision is unavailable. This approach can be applied to natural language processing, knowledge-based population, and relation extraction, to name a few fields. It essentially reduces the need for manual annotation. It enables the system to scale to larger datasets. The system's seamless integration with existing neural network architectures widens its applicability in real-world scenarios.
Sounds promising. As we conclude, I'm curious, Ivo, what should our audience look forward to in terms of future research?
Great question, Mark. Future researchers can explore the extension of this framework to handle more complex logic programs and structured data. This could mean the development of sophisticated embedding techniques or integration of additional optimization algorithms. Furthermore, evaluating the method in different application domains can shed more light on its strengths and limitations, guiding future improvements.
Fantastic insights, Ivo. A huge thank you for shedding light on differentiable logic programming for distant supervision. I'm sure our audience found this illuminating. Till next time, stay curious and keep exploring the wondrous age of AI, blockchain, and quantum computing. Over and out.